Hello and welcome to a new video series where I want to show you an introduction into the theory of distributions. Here in part 1, I want to start with the motivation for this new topic. When you start with real analysis, then you learn a lot of important concepts. For example, you learn what a function is, you learn what a limit is, and most importantly, you learn what a derivative is. With these objects you can already do a lot of mathematics, but in the end you will reach other fields, for example differential equations, Fourier series, and even the Fourier transform. And now here the problems begin, because for differential equations also some solutions with sharp turns are interesting and important. And there you already know that the notion of a derivative is in some sense too strong to consider functions with sharp turns, because at a sharp turn the function is not differentiable. Therefore we need something new that can also deal with such solutions. So we would say we need something that can deal with more general solutions. Okay, we will talk about this later. Here I want to start with an example, and indeed it's a very famous example. It goes back to the year 1927 and to Paul Dirac. What he wanted was a derivative of a function h, and we use the letter h because this function is most of the time known as the Heaviside function. In spite of having this fancy name, the function is indeed very simple. It is just 0 on the negative axis and 1 on the positive axis. And now Dirac wanted to have a derivative of this function, and you see this is no problem at all outside of 0, but in 0 there is a jump. Hence, in the classical way, we have a problem at this one point. Now Dirac wanted a more general derivative, and he called this one the delta function. Now, more general here means, of course, it is a generalization of the classical notion of a derivative. Hence we can conclude that this new delta function has to be 0 outside of this critical point x equals to 0. However, Dirac also wanted that the fundamental theorem of calculus still holds for this new function. More concretely, this means we can write down for an arbitrarily small epsilon the following integral, which is just an integration around 0 for the delta function. But now we know this is the derivative of the Heaviside function, so we can put in the derivative of h here. And now if the fundamental theorem of calculus holds for these functions, here we have h of epsilon minus h of minus epsilon. Now looking at the graph, we recognize that this is always 1 on the right hand side and always 0 on the other side. So we have 1 minus 0, or in other words, always 1. Now, this may look nice, but we already know that if we have these two things together, this delta can't be an ordinary function. Please recall, this first part tells us that delta is 0 except for one point. So in our language, this would mean delta is 0 almost everywhere. To be more concrete, I would say this holds with respect to the Lebesgue measure. And from this we can conclude that every integral for this function has to be 0. In particular, the integral from before, so minus epsilon to epsilon of delta x, is also 0 for all epsilon. Which means it can't be 1 as we wanted before. So here's our contradiction. Now it gets even worse because Dirac does not stop there. Dirac also wants to calculate with the derivatives of this new delta function. And now we see at this point we have to put a meaning into the symbols here. In order to do this, we will define a new object and call this a distribution. And in the end, delta will be such a distribution. For the reasons you have seen above, we want to calculate as we have ordinary functions. This new notion, distribution, is also often called a generalized function. The overall idea for distributions is that we see these objects as densities. So here you should visualize a one-dimensional rod or one-dimensional bar where we have a mass density. Now in this picture, the delta distribution or the delta function would be a singular density. So a density where all the mass is 1 point. Okay, so let's do a picture for this visualization. The graph of an ordinary function may look like this. Now you should see this as the mass distribution on this one-dimensional rod here. And this means here we have a high density and at this point we have a low density. Now for finding the density in the real world, you would use a measurement device. In mathematics, we then use so-called test functions. So functions phi that should be nice enough, so at least continuous, and localized in some sense. For me, that means they are 0, except for one small bump, and that's the region you measure in. Now, in order to find the mass in that region, we have to calculate an integral. So an integral over r, function f, and function phi. Here we get out a real number, which describes our density here in that region, roughly in that way. And now the idea is that we use a lot of these small bumps, so we get out a lot of real numbers. Or in other words, we have a map that maps all the phi's to these real numbers given by the integral. Or in other words, instead of looking at the function f itself, we can just look at the collection of all these real numbers here. Indeed, that is what we will do in the next videos. We will substitute the function f with this linear map. Now the big advantage of this is of course that now we can also deal with this strange delta function. Obviously we can't draw a graph for this delta function because it's not an ordinary function. However, we have our visualization that it is a point mass, so this means it is 0 except for 1 point, and we have put that point in 0. So here we have a jump, and this jump should be infinitely high. So what does this mean? Yeah, it means if you want to measure with our test functions, you get out the value of the test function at this 1 point. So this makes sense for our measurement devices here, and also for the integral we have seen before for the delta function. Indeed, we generalize this integral here. So now we want to put in a new function, the delta function instead of f, but we learned we can't see that as a real integral. What we have indeed is a generalization of this concept to this linear map. Well, I think that's good enough for today. So now you see the motivation for distributions, and in the next video I will give the exact definition of such a distribution. This means that we will learn what the test functions are actually, and also what this linear map then is. Then, thank you very much for listening, and see you next time. Bye!